started. Hello, everyone. Welcome to yet another CIIR talk series. It is my pleasure to welcome Yi Zhang to the CIIR talk series. She is a professor of computer science at University of California, Santa Cruz, where she leads the Generative AI Center. She has been focusing on information retrieval and recommender systems and even conversational AI systems for many years. She has received multiple awards in these areas, including Best Paper Awards from CIIR, Test of Time Awards from CIIR, NSF Career Awards, Air Force Young Investigator Awards, and multiple numerous actually grants from industry, including Google, IBM, Bosch, eBay, NEC, Microsoft, and the list goes on. I think everyone knows her. I don't think I need to talk a little bit more about this. So without further ado, let's welcome Yi to UMass virtually to hear about learning inner monologue and its applications to multi-round RAG.
Thank you. Thank you for the introduction. It's my honor to give this invited talk. And I'm going to talk about our recent work, the work in the last several years about inner monologue and RAG. And first, I want to share, mention that the work we have done were with a group of collaborators, including my students, industry collaborators, other students, other faculty at UCSC, and even some high school student interns in my lab. I would like to acknowledge them here, especially my PhD student, DG Yang, who has been leading most of the work described here. So I want to first give some background about what we are, like, especially for language model reasoning. You see, language models has been doing extremely well on traditional natural language processing tasks, things like reading comprehension, tagging, sentimental analysis. We are also seeing signs that language model can go beyond language, showing reasoning ability, even in areas like math and logic. And the challenge is that most of those tasks still happens in static information environment. And the real world problems are dynamic. They change, they evolve, and they require models to interact with external information. And that's why researchers are exploring language models that use tools, act as autonomous agents, or even collaborate with multiple agentic systems, moving from language understanding to real-world problem solving. And here is a quick overview about how language model can augmented with tools to work in a dynamic information environment. On the left side, we have different language models, ChatGPT and others. Those are powerful, but they work best when connected to a dynamic information environment. In the middle are tools, right? Things like Google, GitHub, APIs that let language model access real-time data, perform actions, or interact with external systems. On the right side are the environments where those tools operate, and workplace, digital platforms, or online ecosystem. So by connecting language models with tools inside those environments, we enable them to reason, to retrieve, to act dynamically, instead of just generating text. Right? We can view tools as bridges that connect language models with external environment. When we talk about dynamic information environment, we mean in the setting where information and environment are constantly changing. In such an environment, tasks are often complicated, require complex reasoning, and every action the system takes might affect the environment itself. This is especially common in multi-round tasks, like multi-round retrieval-based question answering, deep research, or actionable web agents operating on computers. In those situations, model needs to interact, observe outcomes, and adapt its next step. And the question is, how might language models leverage tools to effectively solve complex real-world problems in this dynamic information environment? Could tools using language model become genuine problem solvers? What are the new intelligence could emerge when language models learn to use tools to solve problems in dynamic information environment? Before we answer this question, now let's imagine what humans do, right? What a rational human like me will do to solve complex problems. For example, I'm invited to give this guest lecture at CIIR. And yesterday, I was sitting at my desk, open my laptop with coffee mug nearby, drinking some coffee before sleeping while preparing this talk. And so I'm thinking, first, those are my thoughts about the structure and the content of the talk. So I want to start with example of inner monologue, then connect it to machine reasoning. And then I can begin to imagine, okay, in order to help the audience to see how inner monologue relates to RAG, maybe I should show a diagram of RAG loop, like query, retrieve, refine. This imagination visualize how to explain it better. And in my head, I begin to imagine arrow flow with my narration when I explain RAG in inner monologue. I spend quite some time preparing this talk, keep on thinking. Once I'm almost there, finally, I begin to think a while, say, oh, I need to know the logistics, which Zoom, and there should be something Zoom link, right? I go to search my email. I read the email. I say, oh, the talk is 1:30 a.m. Eastern time, which is 10:30 a.m. California time. My time, I need to set alarm. So I take actions, checking email, search email, setting alarm. And this whole process the goal is to prepare for the talk. And this process is called inner monologue. And so this inner monologue is a concept from cognitive psychology, describes the internal dialogue we engage in when we think or rehearse ideas, prepare for a complex task. And inner monologue, which we use IMs to represent, is basically the voice in your head, the way we talk to ourselves silently. This is how we use words internally to think, to plan, to rehearse, and to reflect before we taking actions, okay? Or while we are taking actions. So the natural question we have is, can AI learn to do something similar and mimic human-like inner monologue process and do multi-round self-talk with auxiliary modules, tools, or with self? And this natural needs to our work on train AI to learn human-like reasoning, right? This is our general framework we proposed. Here we have a language model-based reasoner. It needs to learn how to perform this kind of self-dialogue. It talks to itself through different reasoning modules while using agents, while using tools, and to explore, to evaluate, and to refine the ideas in order to achieve a goal or reaching a final decision. And when we teach AI to perform inner monologue here, and it involves two parts. One is from the language model's perspective. It needs to learn how to use agents, tools, or communicate with other models, or even communicate with itself, right? How to query those agents, how to gather information, how to reason with those information. The challenge is many agents were not a part of the pre-training of language model. When we pre-train language model, they didn't see those agents. So it has to adapt in real time to those agents. And from the overall system side, this is a system with multiple components. It's about enabling smoothing communication between parts to complete a complex task. But that's very hard. Some agents are not machine learning models, and many operate separately without sharing context. Joint optimization is challenging. And learning inner monologue. So it's not just say, let's teach a language model to think. It's about teaching the whole system to reason and communicate more like a human mind. So to make this happen and make it work, we started a journey. It started back in 2022, 2023, when we asked a simple question: can the language model learn to think like us, to reason step by step with an inner voice? And our first work, Inner Monologue, which is IMMO paper, the first work appeared in Europe's 2023 workshop, showing that it can. By pairing language model with a vision language model and train it through reinforcement learning, we show that it begins to learn how to reason in multiple steps. So interestingly, reinforcement learning approach is also used later in the OpenAI o1 and become a common practice for training multi-step reasoning. OpenAI o1 was released in 2024. As we continue our journey, in 2024, in our CIIR paper, we begin to push it further to teach language model to use the search engine as part of its inner monologue, so that the search engine and the language model can engage in multi-round RAG, just like human would do when they do research and thinking. And later that year, in our Europe's paper, in 2024, we did a very preliminary to begin to use native language model to control a camera, deciding where to look and see in order to answer questions. And so at that time, the system is not just responding anymore, it's actively exploring its environment. And later in 2025, in our CIIR paper, then we focus on giving model a new skill, being self-aware. It learns to recognize what it didn't learn and to require when it's uncertain. This is a critical step. And more recently, in our Europe's 2025 work, we begin to explore imagination and visual imagination while doing inner monologue. The native model think in picture, blending self-talking with visual reasoning. It's a small step towards making multimodality inner monologue real. And now, as you have seen the bigger picture and the journey and how the idea evolves over the years, and let's take a closer look at some of the key papers that shaped this journey and see how each one brought us a little closer to building reflective, self-thinking inner monologue system. And the first step towards our goal, we focused on, that was around 2022, 2023, we focused on building the foundation of learning to inner monologue framework. To verify the idea on very simple multi-agent systems, we start with a typical vision language task, visual question answering. So here in this VQA task, we have an inner monologue. The language model acts as a reasoner, and a vision language model or act as an observer, which language model can use as a tool. When given a question like this, what is the cat doing on the bench? The language model doesn't answer directly. Instead, it begins an inner monologue, breaking the question into smaller steps. It first asks, is the cat lying down or standing up? The vision language model will answer lying down. Then it wonders, are the cat's eyes open or closed? The vision language model answer closed. So by accumulating those sub-questions and answers, the model finally concludes the cat is sleeping. This is a simple but powerful process that shows how inner monologue helps the model reason visually step by step, like the human think aloud while using an eye. Okay. And the whole output is this human readable reasoning chain, and it can be interpretable. And so this is what inner monologue can do for our first task, VQA. And now let's look at how we actually train a model to perform this kind of inner monologue-based reasoning. And we used a two-stage training process. The idea is pretty simple. First, teach the model how to think and how to reason, then help it think better through practice. So in the step one, help model how to think. It's actually, we find it's optional warm-up. We use supervised fine-tuning. At this stage, the pre-trained language model might not naturally follow inner monologue format. So we guide it using examples from human written reasoning paths. This helps the model learn how to think step by step, do inner monologue before we move on a deeper optimization. And after that, we do reinforcement learning. Here, the model practice reasoning on its own, receive feedback based on the quality of its final answer. And through this process, it learns to handle multi-step complex reasoning, gradually develop a more human-like way of thinking. And let's look at the first step, right? This is optional, supervised fine-tuning. And when we do talk about supervised fine-tuning to train inner monologue to do multi-step reasoning and correction and so on, the challenge is human labeling of inner monologue data is very expensive, right? Fortunately, for the VQA task, some datasets has short rationale written by human. And we leverage that and then use GPT models to automatically convert those rationale into conversation step-by-step inner monologue format. For example, instead of the rationale say there is only 1 cup of water or 1 main dish, the model practice asking itself, like how many cups of water are on the table? 1. Is there more than 1 plate? No. And those kind of practice helps the language model internalize the rhythm of reasoning about asking and answering before we move to deeper optimization. Then come to the next step, and this is the most important one, reinforcement learning for inner monologue learning. This is where the model learns through experience. The reasoner, which is our language model, and an observer, which is an agent, is a vision language model, take turns. One is trained while the other remains frozen. Given this visual question like what meal is being served, the reasoner begins its inner monologue. Is there a formal atmosphere? Then observer will say, yes, there are candles and tables. The reasoner will ask, are there any lights on? The observer will say yes. Okay. And for those clues, the reasoner will conclude it's dinner time. Okay. And we apply reinforcement learning to reward accurate reasoning and coherent thinking. Over many epochs, the model learns not just to give the right answer, but to reason more deliberately and logically, asking questions, find an answer, like developing its own internal inner monologue. Okay. More details are in our paper, and I want to emphasize the training reinforcement learning is pretty critical here. We train model using PPO, a very common reinforcement learning method for language model. And language model itself act as the policy network. Choose words from its vocabulary is the action. And the model interacts with its context, receive rewards based on how well its response align with the final goal, final answer, and update the policy to generate better text. In this reinforcement learning framework, the goal is to maximize the expected reward. And this reward has 2 parts. One part is the final prediction accuracy. Right? That's the F1 score between the model's answer, the whole system's answer, and the ground truth. Another part is KL divergence that keep updating model close to original parameters to prevent overfeeding or catastrophic forgetting. And this training balance learning better answer while maintaining model stability. And we tried evaluate this work on 2 data sets. One is Science QA, another is SNLIVE, that's visual entailment data set. Generally, it's identify whether the relationship between given image and the text hypothesis is entailment, neutral, or contradicting. Okay. Our model, IMLMO, performs pretty competitive with state-of-art system like GPT-4 at that time. It's much smaller though. Our model has only 9 billion parameters and trained with far fewer examples. What's interesting is the model also remain interpretable because you see the multi-round question and answer inside the system because it's reasoning through this inner monologue. Okay, and also when we compare it with chain of thoughts and other standard supervised learning method, it performs significantly better. As I mentioned, one good thing about inner monologue is this interpretability. It's basically the model's thought process written out. We can see the process, we can have insight on how the model arrived at a particular output instead of just seeing the final answer. This makes it easy for user to understand the model, and so user can make their choices and decisions with explanation. And also by exposing those intermediate steps, so we can spot and correct errors in reasoning, and make the further improvement about the model and the system. So that's around 2023, and we did get this done, and we learned some really valuable lessons. On the success side, we found that inner monologue process truly helps reasoning. Models that learn to think step by step perform more reliable, and this 2-stage training framework that combines supervised fine-tuning with reinforcement learning works consistently across multiple tasks, right? And there are also limitations though. At that time, our reward function only evaluates the final answer's correctness, which makes training less efficient, and because the learning signal is weak. And we also rely on just a single vision language model as the observer. So it's a single one extra agent. And the number of reasoning turns at that time is also fixed. The model cannot decide whether it has enough. So moving forward, we plan to strengthen the reward function and experiment with non-deep learning agents that can bring complementary reasoning styles and the ability to language model, and further make the inner monologue more adaptive, allows the model actually control when to stop reasoning. So next, let's explore adding a non-deep learning agent that can complement a language model's reasoning. And this is something everyone here are pretty familiar with, a search engine. We can view search engine as a symbolic non-deep learning agent that specializes in retrieval. We add it into the framework. This leads to our CIIR 2024 paper, IMRAG. It's inner monologue for multi-round retrieval-augmented generation. So now let's look at the inner monologue for RAG or IMRAG framework we introduced at that time. The multi-round RAG, here we have a multi-round RAG loop. And this is the iterative process, which we call multi-round inner monologue, where the system continues, cycles through querying, retrieve information, refines retrieved information, refines the context, and generate an answer, and requiring to improve this, improve the accuracy. This is the loop, which we call multi-round inner monologue. And this system is built around 4 major components: a reasoner, a retriever, a refiner, and a progress tracker. And the reasoner acts as a core reasoning component in this multi-round RAG framework with two key responsibilities. Firstly, as a questioner, it learns to propose queries for retrieve relevant documents. It also serves as answerer, use those documents, query, and context to generate the final answer. And questioner, we actually train it, use reinforcement learning. And the answerer is trained using supervised learning. Both are trained using LoRa, which is a technique, a very popular technique that you can efficiently fine-tuning language model. It works by just inserting a small number of new weights into language model's parameters, and only those small number of weights are getting trained. And the refiner improves the retrieved documents by rephrasing and re-ranking them, and then pass the top results to both the progress tracker and the reasoner. And progress tracker measures how well the reasoner is progressing. And during this process, it's used for reinforcement learning. Okay, here are some details about how we train the questioner. Okay. Reinforcement learning that balance overall retrieval quality, final prediction accuracy, and also kill divergence to avoid overfitting or catastrophic forgetting. Anyway, the details are in our paper, and the results is here. Generally, we compare it with different methods, and on multiple data set, actually on the hotpot QA data set at that time, and performance are significantly better than multiple different baselines at that time. And that was early 2024, and here are what we have learned. On the successful side, we introduced a new reward function, give feedback to the inner monologue during the reasoning, help guide multi-turn thinking. We also built this non-deep learning agent, that search engine, which CIIR people are very familiar with. And we have this RAG system that combines language model with search engine to do multi-round retrieval. And overall, the system reaches state-of-art performance on benchmark task. However, it's limited. The IM-RAG works with fixed turns, and it cannot dynamically decide when to stop retrieval. And it also depends on data sets that includes golden documents. Generally, what are the good documents for answer questions, which are needed to learn right numbers of reasoning turns. If you don't have golden documents, it's hard to learn. So while the framework shows strong promise at that time, there is still room for improvement. It's flexibility. And also we want to avoid using expensive training data. So that naturally leads to our next work, that's our CIIR 2025's work, where we extend the inner monologue into a new ability we call meta recognition. Meta recognition or self-awareness. Now we teach the model not just to reason and retrieve, but to reflect on its reasoning path, recognize its knowledge limitation and reasoning weakness. To understand the motivation of that, I want to explain meta recognition and self-awareness. Those are all inspired by human cognition. Here we propose 3 levels of hierarchy of reasoning. First is response generation. It's about knowing what's known. This is where current language model like GPT-4 already perform very good. Right? Second is awareness of knowledge limitation or know what's unknown. This is the ability to recognize gaps in understanding. And the third level is knowing acquisition direction, knowing where to find the unknown. This is about actively planning how to close those gaps. You can use retrieval engine, you can control camera, you can control robots to know how to acquire information. And the second and third levels are what we call meta recognition, and generally it's thinking about one's thinking. Okay. Most models today still operate mostly at the first level, with limited awareness of when the information is incomplete or insufficient, at least not explicitly trained to do that. And developing those higher levels is key for making models more self-aware, adaptive, and trustworthy. And that's the situation we have around in 2024. Okay. So this motivates us to work on having this ability for enable multi-round RAG to have this ability. Wants the language model to know when to stop a retrieval and give an answer. And humans do this very easily through meta recognition. We are very good at meta recognition. We can reasoning in mind. And that's why humans know when they don't know. And this was not easy for search engine at that time. Okay. For example, we have this question, what's the fourth highest peak in North America? The decision on when to stop matters. Yeah. There are two common failures. Just without retrieval or with just one round of retrieval, a language model might give answer. The model is too confident. They give an answer when it doesn't have enough information. Or it will keep on searching and get overloaded by noises and irrelevant information. And those distract the language model and the answer gets wrong. Well, ideally, we wanted to have a stop in the middle and have a good decision on when to stop. Unfortunately, the language model at that time was not reliable in telling its own knowledge boundary or tell when it doesn't know. And this is not a trivial question. It's about knowing that you don't know. It's a fundamental form of true intelligence. And this concept has been recognized by Eastern Western philosophers 2,000 years ago, and as well as great scientists nowadays all recognize this is the important thing to have. Motivated by that, this time we switched our focus from teaching language model to do inner monologue to a different level, to try to use an external critique and to study the language model's behavior without observing language model's internal state. That is generally learning from language model's inner monologue and to critique language model. Okay. So here is our proposed solution for in the context of for the task of multi-round RAG. We introduce self-practice inner monologue learning for multi-round RAG, which we call CIIR. And the key idea is to train a separate critique model to check the knowledge boundary of language model and evaluate both the answer and the reasoning process of the multi-round RAG system. And to achieve this goal, in the first step, remember this ability need to be learned. So we need a RAG system to do self-practice to generate training data. Then we train a critique model to assess both the answer and the reasoning quality from the reasoning trail and the synthetic training data. And then finally, with the help from the critique at inference time, the system is able to do multi-round retrieval and answer the question. So let me first explain the step 3. Right? Explain how CIIR works during the inference time. Here we have a reasoner generate an answer when the input question comes in. Reasoner generates an answer and a rationale from the input question. Then we have a critique, judge whether the response is sufficiently supported by the evidence. If it's sufficient, it returns as final answer, then stop thinking. If insufficient, it triggers another round of retrieval and reasoning. The language model reasoner reformulates the query, and the retriever fetch new documents from the corpus. Then we update the context, start a new cycle. Okay, this is the inner monologue process. So the question is, how can we train the critique model? The key is about how to get data that reflect language models' knowledge boundary. We introduce self-practice, a very cheap way to use seed question-answer pairs to generate procedure labeled data. Okay. The general idea is at each round, here the data is we have question answer and seeds, and our goal is to get procedure label data. The general idea is each round we force language model to generate the answer and the rationale, then check with the real answer. If it's correct, we record it as correct, otherwise we reject. However, no matter it's correct or wrong, we get one data point, and then we discard the answer and rationale and move to another round to get more data points. Continue practice. Move to another round to get more data points, different contexts. And by doing this for many rounds, we generate many procedure data with labels. And if you look at it, it's more like a rehearsal process of what humans do. And we practice trying to give answer, and then we have some run to check the answer and give us labels. And with that kind of label about procedure data, right? And then we can train the critique model. This training is pretty straightforward. It's standard supervised learning. You have input are inner monologue data we get, and output are label accept the answer or reject the answer, whether the procedure is correct or not. And we just train a simple binary classifier, easily optimized by supervised. This is very standard supervised fine-tuning, maximize likelihood of the data. And this training gives us a critique. Before I move forward, I want to explain the design choice we make when we design this. First of all, right, CIIR, this system is a practical solution that can be plugged into any current language model-based RAG system without fine-tuning any RAG components. And this saves time and computing power. Also, it works with both open source or good performing closed source models. And more importantly, the critique changes RAG system's behavior without changing the language model itself, without changing the model's parameter, right? By doing that, you avoid hurting the alignment, like safety alignment of language model from its pre-training or post-training. Alignment is very important for a language model. We avoid hurting that. And second is you introduce this critique more like a peer reviewer who is trained to identify the bad behavior from a third person. So that can avoid self-bias or overconfidence from the language model. Nowadays, language models tend to be very too confident. Okay. And this separation from generator and critique reflect our fundamental principle or believe that real progress comes not just from self-confirmation, but also from trusted external feedback. Finally, instead of relying on expensive manual labeling, the system trains itself. Okay. Self-practice, this rehearsal, helps the critique model adapt to private data or RAG system with very low cost. So those are our design decisions. And let's see, does it actually work? So building on the design decisions, here are the results. Okay, we implemented and evaluated the system on 3 standard RAG datasets, like Trivia QA, Hotpot QA, and 2Wiki. Trivia is very simple task. 2Wiki is a more complex task. And we compare RAG with 8 closed open source baselines. And we found SIM RAG works pretty well. performance compare significantly better than many others. And we also compare our critique model, this very small critique model, with what if we use GPT-4 as critique, right? On simple tasks, they actually perform similarly, but on complicated tasks, training a simple model is like any 783 M instead of huge GPT-4 actually perform better. This highlights the importance of using external feedback as critique. And the power of self-practicing inner monologue data is trained on. We don't have, I'll skip some examples given the time limit, okay? And I want to emphasize, if you look at inner monologue for multi-round RAG, this is our framework. But we can imagine this, that the technique we introduce, like self-practice, self-rehearsal, inner monologue to generate inner monologue data to train the system, doesn't necessarily has to apply to RAG only, right? It could apply to images, mathematical problems, web URLs, okay? And so that it's actually a general framework that can work with other black box multi-round systems going beyond RAG. And this has been verified by our recent work on question answering and the math reasoning tasks. And so what we have learned from our experience so far, in human recognition, rehearsal is actually a process of us mentally simulating actions and reasoning before executing, like what I did last night. And in SimRag, the model actually does something similar. It generates many reasoning traces, queries, retrieve documents, interim answers, rationale, without external feedback. And these traces are labeled as accept or reject based on whether they lead to the correct answer. And the critique model is retrained. So the system is thinking aloud to itself, practicing reasoning internally before learning from it. And the critique essentially learns meta-recognition, recognizing when reasoning is sufficient to stop retrieval or when further thinking is required. And so we think about this self-practice as rehearsal. It's something people do a lot when we do our inner monologue. And just like a human refine their judgment through mental rehearsal, our critique learns from those synthetic practice to recognize when reasoning process has reached sufficiency. And we also applied this to some other applications. For example, recently applied to deep research, generally it's a retrieval-augmented video generation task. Generate high quality video from user request using RAG. Okay. Here are some examples. In this example, users say how to cook a pancake in modern versus ancient settings.
In a modern kitchen, preheat the oven and begin combining the cake ingredients, then carefully place the batter in the oven. In a primitive setting, hand mix the ingredients and cook the cake batter on a heated, flat rock over hot embers.
Here is another example of question. I need help with two things. I want a recipe to make pancake from scratch, and I want to set a theme for pancake and need suggestions on how to incorporate other ingredients. The theme is Halloween.
Mix dry ingredients in one bowl, wet in another, then fold them together. Pour batter into a hot pan, flip when it bubbles, and cook until golden. Decorate pancakes with Halloween-themed toppings and serve on a festively decorated table.
So we can show this approach can be applied for deep research and generate video to answer user request. Okay, let's move forward. While working on inner monologue, we begin to ask a deeper question. Can language also think visually while doing inner monologue, not just talk to itself in words, right? So far, we have been doing text reasoning. And what if AI can do, can imagine? generate its internal image and guide the reasoning. And that naturally leads to our 2025 UMass paper. In this setting, we extend the concept of inner monologue to VQA setting for image retrieval. And the task is giving a text or image, the system issue a query, retrieve image, refine the query based on what it sees, and repeat this process. So instead of the model talking to itself, we now let the model think visually. Here, a model is here, we use an image generator actually as core part of the system. We let the model think visually, have an inner monologue between the model and the image retriever, and have the system have a dialogue between the model and the user. The model will generate some hypothesis images from the query. The query is text, and the model generates hypothesis image from the query to visualize what it imagines. And it sends the image to retriever, and the retriever will do search, image search. And it also sends the image back to the user who issued the query. Then the user receives the image, and then user can identify discrepancies of what the model think and versus what the user think, and then modify the query. This form a dialogue between the system and the user and the inner monologue within the retrieval system. And we call this process generative mental image retrieval, where visual feedback plays the same role as inner monologue in text-based reasoning. And we evaluated, compared it on 4 data sets from MS COCO to facial recognition to Flickr or to clothing domain. And it consistently outperformed all baselines. The results actually shows the approach has pretty strong cross-domain robustness and handle fine-grained visual details. And that in those cases, a lot of time text itself cannot capture. So far, the takeaways we have is now we can think in multimodality, right? Humans often see solutions before explaining them or before reaching them. And by thinking visually and together with thinking in text, we have complementary thinking ability. The image can encode spatial relationship and composition pairs, all those things. Some of the information image can encode and text cannot. Okay. And we can use image to ground abstract reasoning, visualize ambiguities, enable self-correction and comparison and regeneration so that the model can see, imagine, and explain in both ways. So that's the major things I want to talk about. And when I want to conclude to emphasize, inner monologue is a pretty powerful ability for human and also for AI. And the ability to think, to reflect, to rehearse, and to know what it doesn't know is very natural for human. It's a learnable ability, and it's independent tasks and domains. So we should try to train it for AI. And when we think about this as inner monologue, it invites very new questions, and our research learns changes. As illustrated in this talk, all our papers come very naturally after we call it inner monologue, because it's very natural to ask how to learn it, how to find new information, how to be self-aware and measure the quality of inner thoughts, not just the accuracy of the answer. What rehearsal means from AI. Can this loop extend beyond text into visual thinking or embodied reasoning? Those questions come very naturally when we start to call it inner monologue. And those questions pushed beyond benchmark optimization or beat some performance. It pushes us towards AI recognition as our research journey shows. And earlier we have discussed the 3 levels of cognition, right? Knowing what's known, Generally, that's multi-step reasoning, and another is knowing what's unknown. That's reflection and self-awareness. And the third level is knowing where to find using retriever or control cameras, control robots. And those three levels of things come very naturally when we call it inner monologue. And we also, from our experiments, we also learned that language model, the whole system can develop inner monologue ability in multiple ways through reinforcement learning, imitation learning, in-context examples, and even self-practice and rehearsal. So the model can generate its own synthetic training data. And there are quite a lot of ongoing work we can do. For example, we are our multimodal inner monologue work is very preliminary, and we can do much better. And in the future, we can explore new domains and tasks where inner monologue can help AI. And the inner monologue ability can also further be advanced. And it can also be linked to other ability of human intelligence. Those are all the future work. And that concludes my talk. Thank you. And if you have any questions.
Yeah, I have a question about, you mentioned that, I mean, it seems like the critic module is very critical in the entire pipeline. Like that sort of teaches the actual LLM the knowledge boundary, for example, what it doesn't know. So you mentioned that there's like a QA pairs that you use to train the critic itself. And I was just curious, how is that QA pair data set curated? Is that manual or is that somehow automated? I was just curious about that.
Oh, so we just collected the QA data set from elsewhere, right? As CIIR people, you know, there are a lot of benchmark data set. We just get those data.
Okay, so there will be a lot of QA pairs where it answers correctly, and there'll be, I'm assuming the incorrect results will be pretty sparse, right? Given the LLMs are pretty good at mostly answering correct answers. The hallucinations are more of an exception than a rule these days. So in the QA pair data set, I'm assuming the most cases would be correct answers. Is that your experience?
Yes, so the Q pairs are all correct answers, but we generated, the key here is we generate a lot of negative training data. Actually, our final procedure data are dominated by negative failed examples.
And those are manually curated, those negative?
No, it's just by comparing whether the procedure, this inner monologue, if the system does an inner monologue, produce an answer. If the answer is not the same as the benchmark data set answer, we label it as negative.
I see, I see. So from your results now, for example, once you have trained the model with your the critic model, so how does the sort of like its knowledge about this knowledge boundary, like where it doesn't know? So if you ask a question and that it does not know the answer about, what does it respond with? What is this answer once the whole module is trained? Does it say, I just don't know, or what does it say?
It will go trigger another round of retrieval.
Okay, okay.
So this is a multi-round RAG system.
I see, gotcha. And my last question is, you mentioned that going forward, you're looking at incorporating some symbolic model into the pipeline as well. So I was wondering, are you thinking in terms of like a knowledge graph or some sort of architecture along those lines?
Those are all part of it. We already have integrated knowledge graph into deep research framework.
Okay.
And in general, we are looking at all kinds of tools and all kinds of different models.
Okay. Are you using some open source knowledge graph, or did you develop your own?
We don't develop our own. Actually, the knowledge graph software we use other people's developed. So we have been building knowledge graph on the fly ourselves, but we also use some existing knowledge graph.
Okay, wonderful. Thank you so much.
You're welcome. Yes.
Thank you for the interesting talk. Any questions from the audience here? I have one question. that basically more generic questions about the definition of inner monologue. So this is space of reasoning in large language models and basically agents in general is kind of growing really fast. And but I know that some of the research you presented are even pre-GPT-01. So I'm wondering, how do you see the current state of the art in this space? So do you, first of all, the reasoning models we have, the tokens they generate or the content they generate, do you consider them as inner monologue of these LLMs? And if yes, what's the current situation? What is missing?
So let's look at the state of art first. Okay. I think a lot of state of art on reasoning is along chain of thoughts, right? Which is very famous. It focuses on the reasoning trees, okay? Step-by-step reasoning. And then there are quite a lot of follow-up about further improve chain of thoughts. Like a chain of trees and all kinds of things, or even try to learn that. And so you can view chain of thoughts shows the past, and inner monologue is more about simulating the thinking experience. Actually, our inner monologue work was originally motivated by chain of thought. Even before chain of thought paper were officially published, I invited Denny Zhou, the author, give a talk in our university early in 2022, and we immediately realized this should be an ability to learn the way have this inner monologue. And when we think about inner monologue versus chain of thoughts, I think both are technically going to the same direction. Except the work under inner monologue framework, we think is very natural. You naturally have those things coming, right? Because that's what humans do. Oh, sorry, can you say your last question? The other question is?
I think you basically answered both questions. Thank you. Any other questions? There is, oh, Beverly, please go ahead. You should unmute yourself.
Okay, thank you for the talk. It's really nice. You keep talking about natural and what humans do. I would like to know if you're going to look at the cognitive sciences out there and figure out what kind of training humans use to train people. In other words, there are lots of systems, mastery learning, for instance, where you ask a person more than once, and then you look at the gap between the answers that a person gives. Or a second one is called curriculum training, where you organize the topics from the easiest to the hardest. So do you think you will move to look at cognitive science and try to teach the LLM according to these principles?
Good question. As you probably won't be surprised, we have been looking at cognitive science and motivates the work. And it's a debate. Although along this line of work, natural is because we are motivated by cognitive science. But on the other hand, the other side of my brain was thinking, do we need to train AI like how we train human? It's actually a question. For example, do we really want curriculum training for AI? Or maybe we should solve AI even more complicated problem first. And to net it just self-practice, right? Instead of training level 1 math, you saw it IMO math. Okay, so those are research questions. I don't have the answer, but those are good things we are thinking. Yes.
Great, thank you.
Okay, thank you so much again. We are right on time, so let's thank the speaker one last time.
Thank you for inviting, and it's nice to see some familiar faces. Bye.
Yeah. And thanks everyone for joining. So we meet you in a minute in the other Zoom link. And everyone, have a good day.